Okay.
Is there anybody? Our next speaker is, and probably the last speaker in this row, Muhammad Wasim from Intel Labs. Over to you. So you'll use this podium, right?
Yeah. Good morning, everyone. In this presentation, I'd be talking about OpenOmics. It's so. So my talk is about OpenOmics. It's a framework for accelerating digital biology. So OpenOmics is a phase of our effort to advance research in digital biology. So my talk is going to be revolving around various facets of OpenOmics. So we are at the epoch of digital biology. It's like a conversion of different revolutions starting from our ability to measure biological system at a very good resolution and different kinds of data, the multimodal data. On the other side, advances in cloud services. So cloud has gotten bigger, better, efficient, and now we can store huge amount of data, collaborate on that data, and use it for various purposes, right? So it's available on demand, right? So cheaper and faster compute. And then advances in AI and ML side of
Actually, you are not audible somehow. Maybe you can speak on.
third revolution that is happening is in advances in AI and ML. Still not? Is it better?
Yeah, that's the.
The third revolution is happening in AI/ML side, so they have the ability to analyze huge amount of data. Right? Fine now. No? So this is it. Oh, kidding aside. So yeah. So all these three verticals, right? They are revolutionizing digital biology or biology, I would say, right? Huge amount of data processing and everything, right? So what do we do about it, right? So there is a massive appetite for compute, right? So with all this revolution happening in biology, we have the ability now to understand the mechanics of various biological processes, right? And that puts pressure on the compute. So, and the other side is now we have that ability, we can go and intervene in the biological processes, right? So for example, drug discovery, protein designs of different kind, right? We can go and synthesize our own protein because we have that ability because of this revolution, right? And it's an iterative process, right? So as I was saying, on the both sides, you can see there's a huge search space here, and there are billions of genomes going to be sequenced, right, in the coming decade. And right now, the processing power, right, if I just talk about variant calling, the processing power is just less than 10 genomes per day, right? Even with that, right, and billion scale genomes, our supercomputers won't be enough to handle that kind of compute, right? So we need to be preparing for tomorrow. If we don't, then we'll lose one of the verticals. Okay, so with that, right? So how do we solve this, right? So we need to develop novel methods and algorithm in different domains, right, to propel this kind of problems, like to solve this kind of problems, right? And once we have that kind of ability with the methods and algorithm, then they will naturally lead to software-driven processor architecture design, right? So our computing needs to be evolving with all these advancements, right? So to that end, right? So we are preparing for tomorrow. Lots of data require lots of compute. What do we do? So right. So we are preparing for tomorrow, and we are proposing OpenOmics. It's a framework for all digital biology needs, and some of it can be applied to other domains as well, right? So I'll go into more details of that, but it's a one-stop solution to all the computational needs of digital biology, right? It's like and we have a grand vision with this software framework, and that I'll cover subsequently, right? So it's a one-click open source software stack enabling workflows, right? And those workflows can span any kind of omics. Right now, start with genomics, transcriptomics, proteomics, so on and so forth, right? And it's open source, it's available. Users can go look at it, try it out, and of course I will cover the details of it, right? So overview of the framework here. So it's a 3-layered framework. On the top there are various pipelines, right? For example, variant calling pipeline, single cell pipeline, alpha fold pipeline, right? And this pipeline, you'll need tools, right? It involves tools. So we have all various tools available in this layer of OpenOmics toolkit, right? Starting from read mapping all the way to protein folding involving tertiary analysis, variant calling, data processing, right? So this pipeline, as I'll describe, can assemble this tool and create a pipeline, right? And then there's a third layer, which is basically has building blocks, right? So you can, there are high performance building blocks available here, right? And you can go and use these building blocks to create tools and then create pipelines. So in that way, whatever you build on the top of this will be high performant, easily available, and so on and so forth, right? And then we have, in this layer, we also have AI building blocks also, because AI is emerging, as I said in my previous slide, right? Has a huge ability to process large amount of data, right? So we also have distributed framework. If the data is huge, compute details, you cannot solve it on even one single server gate processor, right? Then you will need multiple nodes like supercomputer and big clusters, right? So how do we enable that? So we have this library over here, and then there's a data management part here. With huge amount of data, you will need data management. So it's an all-encompassing framework, right? And you can see at the bottom, no issues. It can run on multiple hardwares and different facets of computing here also, right? So in the previous slide, we get a feel that it's just a software framework. I can use it and run it on any system and be done with it, process my data. But that's not the limit of it, right? The whole vision behind this OpenOmics framework is to be very, very holistic, right? So whatever pipelines or tools we have in this framework, right? They should be highly performant first, and they are. And
switch.
I can use it. Yeah, so they should be highly performant and very, very easy to use and deploy, right? I can say from what I heard from our domain expert, like they want just very easy one-click solution to run all this analysis pipeline, very, very minimal effort on programming or maybe whatever computer side of it, right? And they should be easy to run, and that's a very, very important criteria. If you have performant tool or performant pipeline, but if it's not easily usable, right, what's the use of it, right? So that's a big facet of OpenOmics, that it should be highly productive, right? And then we have targeted user and tailored kernels and interfaces for them, biologist, bioinformatician who wants to basically deploy different tools in a pipeline, and then computational biologists who can build quickly, very quickly, new tools, right? I have bowtie, can I do bowtie 3 on that, right? Can I modify something in some kernel and get a better alignment tool, right? Then other facets, right? So for example, performance benchmark. So through OpenOmics, we created a performance benchmark called Genomic Suite. It can be used to just benchmark various architectures, which one is better for this kind of workload and which one is not, right? And then whatever we learned through this exercise in OpenOmics, it gets translated into various architectural recommendations. So for example, through this, we came up with accelerator called GenDP, which I'll be talking about, and then breakthrough applications. So talking about the performance side of it, so what we do generally is we identify the workloads or areas that we want to work on, right? Various pipelines or tools or whatever, right? And then we apply this iterative strategy where we profile, if the tool is already available, we take it, profile it, apply parallelism, right? Various kind of identify what are the architectural bottlenecks, is the current architecture suitable for that or not, right? And based on that, if we need to improve our hardware to make it faster, right? We do all such kind of things. So it's a complete stack, right? From top to bottom to get best out of, or to get the best solution to your problem, right? So the second side of it, right, the productivity I was talking about, and so there are three branches we are looking here, right? One is from the domain expert point of view, the biologists, right? What they want is just use their data, data and run standard pipelines, for example, dperiod, right? And they are not interested in any, of course, low-level understanding or tinkering or changing of the tools or pipeline, right? So they can just go and interact with the pipeline layer, which was this one in my previous slide, and just do one line run of that, right? So very easy for them to run, right? That's what I meant by productivity, which is one facet of it for domain expert, right? But if you want to go and customize pipeline, right? So we have another layer below the pipeline layer, the toolkit layer, right? If you want to go or try out different tools which are highly performant, right? You can do that. You can play with that, right? And you can create your own pipeline. So that was the second layer. Now that, so for example, this is a very good example of that, right? So we have short read pipeline here using diff variant. We have long read pipeline here. The input is again read and output is variant here. If I want to build such kind of pipeline with BWMM, then sorting, and then diff variant, I can just take out whatever tool I want from here and put it. So in each boxes, right? For example, here also, you can directly use that, right? And then for long reads also, right? So if you don't want to use BWMM, Minimap is a better offering for long reads. So why not just go and just plug it in here instead of this one, right? And create your own pipeline. So that's our vision, right? That should be how it should be, right? To get the best out of this framework. Then third is for the tool developer, right? So if you want, again, I was giving an example of bowtie, right? If you want to just change some part of it, for example, the alignment part or for the seeding part, you can just take various kernels available here, right? The building blocks in this layer, modify according to your need. They are highly performant, so hopefully when you modify it, you would be able to retain the performance, and then you can basically develop your own tool, right? So that's our vision, right? Quicker and faster progress if you want to try out something new and do something, for example, new thing in variant calling, right? You can quickly do that. So from now onward, what I'll be doing is I'll be describing what all is in their OpenOmics framework, right? And what they do, right? How they are. So I'll start with the pipelines, right? So there are very standard pipelines here. The short-read pipeline. So I was already talking about the variant pipeline. Again, mapping, sorting, and then some deep learning magic here, right, to create variant calls, right? We see. So what we did is we wanted to basically have what we did is we optimized various parts of it, right? In this pipeline, basically this part, right? And then on the top of that, what we did is we scale the pipeline from 1 CPU to 32, right here. And of course, to do that, we needed to apply some multi-node communication algorithm, right? So we did that here. So we implemented it's using MPI for pi and applied various HPC magic to it, right? And with that, we were able to, so initially when we picked up the pipeline, right, it was at 2 and 2 seconds. And then as we increased, we did some optimization on the just one node, right? We identified some of the inefficiencies, and then we improved from 212 to 90. And then we scale it down, right, to 32 CPUs. And at the end, whatever was getting solved in 2 minutes is getting solved in six minutes, which is pretty awesome, right? So again, this question, this is answer to the question, right? If I need very minimal time or quick solution to my, so I have this fast view file, and I just want quick variants out of that, I can use this pipeline, right, in multi-nodes, and it substantially improves over the previous number, which was 16 minutes, right? So speed matters, and OpenOmics provides that. And of course, as you can see, this is a throughput, right? So with this speed, we are able to process 236 genomes per day using this at 6.1 minutes per run, right? Which is again substantial increase because the previous number is below 100. Moving on to the second part of it, right? So we looked at DNA, now we'll go to RNA. There's a single cell pipeline here. I'll just describe what all we have here, right? So we picked up ScanPy pipeline and we optimized various parts of it, right? Understood the compute characteristics and accelerated that, right? It's a widely available toolkit, so whatever you do will be impacting or used by many folks in the community, right? And again, the same story, we were able to get significant speed up, right? So these are all Intel server grade machines except A100, which is a GPU. So across these different machines, right, using latest Intel offering of Sapphire Rapid server grade CPU, we were able to get down 18K to 279, right? So again, right, you can use this speed to just quickly analyze and get meaningful things out of it, right?
So can I ask a question?
Yeah.
So there's Intel Xeon ICX that you have here, right? So the first baseline and the OpenOmics also says the same thing. So what is the reason for the big, or what is the main reason behind the big speed up?
You mean last two bar, right?
No, the first one is Intel Xeon ICX baseline. And then the third one is also Intel Xeon ICX. So it seems the hardware is the same, but only the software implementation is.
Yeah. So here the software is not taking advantage of multi-threading. So you have many more cores, right? These are server grade CPUs. There's just one aspect of it, right? There is a architectural efficiency also, right? So all that has been applied to that, so that at least you use the correct way, architecture in a correct way, efficient way. So by just doing that, we got to 408, and then we improved CPU version. So ICX is the third generation, and this is the fourth generation latest offering. The hardware to hardware improvement is this.
But the tools are the same.
Tools are exactly the same.
Enable multi-threading in those tools.
Yes. So as I said, multi-threading is just one part of it. There are many aspects to that.
Okay.
Is the RAM consumption same?
Sorry?
RAM consumption is the same?
Yes. So our goal is to keep whatever the baseline tool as it is in terms of memory, in terms of output correctness, right? Everything, so that you can put a drop in, replace one to another, right?
So I have a similar question. So A100 is a GPU, right? So how many cores it has?
For different kind of precision, different number of cores. So in terms of flop, I can tell you, right? So A100 is FP32 precision is around 10 or so teraflops. So it has lot of compute power.
So should it not be faster? Even
So-
in the previous slide you showed that it is slower than 32 nodes.
Right. So, so the thing about this is it's all about architecture, right? So you have workload, you have characteristics of the workload, the cache usage, the speed of the code, right? The frequency, and how efficient are the cores. So even core to core, there's a big difference. The single thread, right? So there are multi-level aspects to that, right? And it turns out that whatever characteristics these loads have, workloads have, for those characteristics, we found that even for, I'll come to that, but we found that CPU can perform better. So these are like, this is not our number. This is,
So see, for leveraging GPU, we need to offload the job entirely to the GPU. Then only you'll be able to leverage it, right?
yes,
Even with the previous case, which was surprisingly 16, right? But
See,
the
the
hardware
problem is this single cell auto sequencing pipeline is a conglomeration of different tools, and even ScanPy is not parallelized inherently.
Right.
By default, it is not parallel at all.
right,
And also, if you want to do that, it's not like they don't have their own algorithm, right? It's not an algorithm. It's a combination of several different things, many of which are inherently non-parallelizing.
Mhm.
So I don't know how that will be taken. That will be a big.
That's what we did, right?
challenge that
So
we'll have to
that's
solve.
what we do, right? So you have in this big bar, right? If it is difficult to parallelize, let's say if I just write OpenMP threads, simple one pragma, right? I don't know whether you are aware of that, but it's a one statement, right? You may not get speed up because you need really good algorithm tweaks to do that. Maybe new algorithm completely, right? Just the way of implementing it, not the output and input, right? So a lot of things are in there. It's not like having more core or more flop not always translate to better performance. The architecture has to suit the characteristics of the application.
But if it's data parallel, you can easily upload that to the
Yes,
GPU, right?
yes, yes.
But what is happening here?
But there are many single thread. So for example, if you have a lot of logical statement, I'm just giving an example, right? There are logical statement in your code, right? So in that way, parallelism won't help you. But CPUs had that power, even though the SIMD parallelism which CPUs have, even if they don't work, still the cores are faster.
But you can do a depth analysis and see whether it will actually give you the requisite if statement depth, if this nesting is too deep, then only you will have more speed up.
Yes.
So the shallow depths, then you should be fine, right?
Yes.
So
But still, again, CPU would do better, right?
No, CPU is designed to be that, but you have so much hardware just lying there, right? So that's what I'm asking. Why have a 800 there? You cannot use it.
So what is also Clara Parabricks?
So yeah, so it's like again a library which is specially designed for omics workload on GPUs.
Okay, so I was wondering what will happen if you run OpenOmics on 800. So that comparison would look very interesting.
Again, the parallelism is different, right? Here,
Right.
here's, for example, SPR has 56 cores, right? And this guy has like thousands of core, right? So the parallelism would be different, and then the way you access data. For example, if your application is accessing a lot of data, for example, if there's a latency in the data, irregular memory access you are accessing, right?
Okay,
Then
we'll continue with the talk and then we'll come back. But this is very interesting, that's why we interfered.
sure. All right, so I need to move faster, I guess.
Can I make one point before we move on?
Yeah.
All the NVIDIA numbers shown here, all the GPU numbers shown here are not our, we have not conducted those experiments. They are taken directly from NVIDIA streams. So whatever they have done, if they have done a good job or not, that's up to them, but we have taken it direct. So it's not our number.
So 800 is like NVIDIA numbers.
Yes.
Okay, the commercial package,
Parabricks is NVIDIA's commercial package, where they have accelerated the bio workloads on their system, and we are comparing directly with them.
So yeah. Okay, so the third part, which covers the folding, protein folding. So I don't need to describe this slide. Hopefully people are aware, right? So AlphaFold 2 is all over the news, right? And almost with 92.4 of score, it has beaten everybody, right? So it is like the software to go for doing protein folding, right? So with that huge demand, we again went to AlphaFold and understood again the same thing, characteristics and whatnot, right? And learned from it, right? At a very high level, the architecture looks like this, right? We have pre-processing in here, where they take the amino acid sequences, search to the database, and get there again the similar structure, similar sequences, similar structure, and then in the post-processing, which is again pure deep learning based engine, right? Takes the output of this guy and converts it into 3D structure of the protein. So at a high level, this is how AlphaFold works, right? We again looked at both both the parts of it and did optimize on CPU, right? So across various protein or amino acid lengths, right, starting from 91 all the way to 6K, we just compared this our OpenOmics optimized one with the baseline, and we are able to get better speedups, right? So in that way, it's a good news that here also OpenOmics has the best solution available. But this is on the latency part of it, right? So you give a sequence and how much time does it take to convert that sequence into a 3D structure, right? But if you go into throughput mode where you are providing many more sequences and you run them in parallel to convert them into 3D structure, so in throughput mode again OpenOmics is able to get much better run times, right? Lower is better here. Again, this is on Intel latest offering, Sapphire Rapid CPUs, which has 56 cores. Moving on to the tools part of it, right? So till now I was talking about the pipeline part of it. Tool part of it, I'll just quickly cover what offerings we have and what we did with that. So this is a short read sequence mapping tool, right, called BWMM. So what we did is again we checked out BWMM and figured out that okay, it has these two kernels, seed and extend, which is pretty much the standard strategy when you do sequence mapping. And then we figured out various aspects of it, right? For example, for shading, it uses FM index, which is highly irregular memory access. So it becomes like if you are going continuously to the DRAM, right? CPU is going to DRAM for data, you are bound by the latency, right? So then how do we deal with that, right? For such kind of, and that's what I was talking about, right? So if such kind of workload you have different CPU suiting for them, GPU or CPU, right? And then for the extension part, it's chaining of seeds, and then extension part is the Smith-Waterman algorithm. It's again modified Smith-Waterman because it has band, and then band is again variable, varies, its size varies as you process the DP matrix. Again, this is at the face split quaternion is regular compute, but if you put all the heuristics, it becomes very difficult to get any speed up out of that using vectorization, right? So we had that challenge when we started improving the BWMM, right? And BWMM is OpenOmics offering. So with all of this, whatever speed up we got, in addition to that, we also applied a very novel strategy here using learn indices, right? Which is a deep learning based solution for sequence analysis. We call it LISA, right? So it's a first of a kind study where we used deep learning to do sequence indexing and searching, right? And just by doing that, this stage, right, the seeding stage, we were able to speed up by 5 to 7x, which was again addition to whatever we got earlier, right? So if we look at what is that, how does the acceleration of BWMM looks like here, right? So overall, we were able to get 2x speed up, and I would say 2x is really not so good speed up, but it was very well received because people were looking for speed up, and for this tool especially, any speed up was welcome, right? And 2x in that sense is a real good deal there, right? It's again the same thing, right? It's open source, and you can just put in wherever you want, and it should perform as in terms of accuracy or output exactly same as the original BWMM. Just a chart showing how is the performance, right, against current solution, as in best solution, current best solution, which is again on GPUs. And then we had the baseline here, right? And against this baseline, we were able to get to 68.2 using the Sentient solution, which is which I skipped, I guess, but it's another offering of BWMM, right? And this is OpenOmics Md, which is at 81.8. So these are genomes per day, processed genomes per day. It's a throughput, right? Higher the better. And we are at 81.8, but the best is 84.7 here, right? But you can also look at the difference in the hardware here, right? So everything is 2x Intel CPU, but it's 8 GPUs, right? So if you are putting more hardware, you will get more speed up, but it's not on parity, right? So in that sense, this one is highly efficient in terms of money, right? And if you put 8 of these, I have shown in the previous slide, if you scale using MPI, we get this 81 to go to 236. And as I was saying, right, so all this work was very welcomed by the community, so they adopted in various studies, right, all scientific and production units, production pipelines in various, for example, Shanghai, right, so they have adopted it. So we also did some work on long read. Because of time constraint, I won't go into detail of that, but it's present in the OpenOmics. The tool is called Minimap2, and we again use machine learning and various architecture-aware optimizations, right? And we got 1.8x out of that, right? So again, as I was saying, any speedup is welcome in this area. Moving on, the third layer of it, right? So I was talking about pipeline, I was talking about tools. Now let's talk about the building block, which is the bottommost layer, right? So in this space also we have worked quite a lot and published a numerous paper, right? So I wouldn't be going into details of that, but if you are interested, you can just browse through the papers. It has fantastic details in that, going to various depths of architecture if you are really interested in that, right? Moving on to the AI building blocks of building block part. So I just want to touch upon the AI for graph because it's a very hot topic, right? And people are really applying AI on graph for various application in biology, right? So one very interesting example here is it's for drug repurposing, right? So these two graphs right here, you have target disease like this, and you have drugs. So whatever drugs for this disease, you already have the connection between them, right? And then if you want to figure out whether this kind of drug work for this disease, you can do AI for graph on this side and figure out whether it's possible or not. So for example, in this case, these people did that, right? And they found that, okay, this link is possible, right? So this drug for this disease is possible. It can be applied to that. And the fitness, right, is 85%, which is high. But on the contrary here, right, in scenario bits found that, okay, the link, but the probability or likelihood is only 21%, so drug may not work, right? But according to some threshold, we can pick what is good or what is bad, right? But this kind of work is happening in this space, right? And then again, what do we do? Why are we bothering, right, in OpenOmics for this? Okay, this solves biology problem, but these are also computationally intensive problem, right? So I'll talk about what they are and why they are computationally intensive, right? So in GNN, it's an architecture, right? It's one of the models of highly popular model for AI and graph, right? It's called graph stage. The graph is little bit, I would say, different, right? Because you have nodes and edges here, but there is a data, vectorized data per node. It's called embedding, right? It provides much more information about the vertex. And then you use this data, and then you use this neural network architecture, right? Because it's a fully connected layers of neural network. And then what you do, yeah, you basically go and apply graph stage, right? So the main point I want to highlight here, and I don't want to go into the details of it, right? There are two major operations here. One is called aggregation, right? So in aggregation, basically each node goes to its neighborhood, right? All the neighboring vertices and gets the embeddings from them and do some operation on them and creates a new embedding for itself, right? And similarly for all these vertices, and it goes for multiple hops, right? So you can see all these vertices are connected to this guy, and these two guys are connected to these guys, and similar story goes for other vertices also, right? So this is the core of it. As you can see, if the graph gets bigger and bigger, it's not just the nodes and edges, you have these things also, right? So your graph won't fit on a single node, even on a surrogate CPU, right? Okay. So yeah, so we did apply parallelism to that, right? Single node optimization, again, because we wanted to have an efficient solution, right? Then only we can learn what is your architecture is not capable of doing, right? So we did pretty good work in this space, right? By 2x speed up here, 3.6x speed up here, and then we scaled from 1 node to 128 nodes, right? Again, these are surrogate CPUs, but these are CX, which is second generation Intel CPU. Yeah, as you can see, these are big bar. We needed a very specialized machine to just try and get these bars, right? If they are not available outside. But since we had that, we tried that, and we saw that, okay, we can measure how much speed up we can get out of this, right? So we did that. This is for full batch training, right? Where every vertex talks to every other vertex. You don't compromise in your neighborhood, right? But there are some applications where you can sample because you want to reduce the computation. You can sample some of them iteratively, right? And then do the same thing. And in that space also, when the computation gets bigger, you go to multi-node, right? So we did that for graph stage as well as GAT. There are two different popular models for doing GNNs, right? Graph neural network. And again, we were able to get pretty good speed up. We beat the computation, and as you can see, it's in second. It's a graph size is like 100 million nodes and 3.2 billion edges, and each node has like 128 floating-point feature vectors, right? So it's a big graph, and we are able to apply multi-node on that, right? So with that, I'll just talk about what. So we created a benchmark, right? Out of OpenOmics studies, right? So this benchmark is useful if you want to evaluate any architecture, how good of that architecture is for. As it's for genomics workload. This is genomics bench, right? Not covering complete omics. But out of this exercise, we found 12 representative kernels spanning shorted, long-range, sequence spanner, LLC pipeline, right? And out of these 12 kernels, we picked 4 deep dynamic programming-based kernels, right? For example, Vandersmith, Motman, PairHMM, and other ones, right? We did that. We studied them. We created a specialized architecture, right, to accelerate for them, right? So that we can solve this problem very, very quickly. So this is like architectural evolution or architectural improvement because of what we learned for various omics kernels, right? And again, so we did pretty good job with this. We got real good speed ups here, right? You can see 157, 132 over CPU and GPU baseline, right? So this paper is published recently published in ISCA. If you are interested, you can go and check it out. But yeah, that was about 4 kernels, and of course the journey continues, right? We have other kernels, what we can do about them, right? So I just want to finish the talk with just one final slide, right? So we have done architecture, we have done framework and everything, right? Helping users and whatnot. But there is one big stuff missing, right? How do you propel science? How do you advance science using this framework? Because that is one of our vision, right? So these are 2 projects of various projects we are working with. Working with Mila. So Mila is a Montreal Institute in Canada. They have world-renowned experts working in AI space, and they do biology also. So we work with them, and one of the problems we are solving with them is exascale search for drug molecules, right? the search space is pretty huge, right? And then you go and search through that space and find out, right, what are the drug molecules that I am interested in, right? So huge compute again. So and then second one is again protein representation learning, and in both of these, whatever work we did with GNNs and other stuff are getting used directly, right? So just wanted to highlight that OpenOmics is also advancing as we speak, is also advancing science. So with that, I'll finish my talk. Thank you everyone for your attention. I just want to acknowledge my colleagues and amazing collaborators. And I need to show this. Thank you.
From one.
No,
you can. Just pulling.
So FPGA was one of the hardwares you showed in one of your slides, but I didn't see any implementation of FPGA accelerators.
Right. So this is like a work in progress, right? OpenOmics. So what we did is we have the best architecture available, which is CPU, because their productivity is very high, right? So we started with CPUs and put it out there, right? FPGA is in plan, but again, if the demand is high for FPGA, we'll consider doing that, right?
No,
So,
as far as I don't know if they're available, there's a company called Edico Genome, which actually implements the whole,
Yes.
variant finding pipeline on FPGAs, and they are the best sellers.
right.
So where are you on this game?
So FPGA, the biggest problem with them is the development, right? If you want to develop something, it takes long time, right? Of course, the code will be performant, but so unless and until you are sure that this is the kernel I want to code, you can go and do that. But the development time is high, right? So of course that is on the agenda, but you cannot directly jump to FPGA because it will take a lot of time to come out, right?
That I understand, but the reason I'm asking is that the slides you showed, so Intel has their own FPGA, whereas GPU, we are not manufacturing GPUs. So so you are better off actually accelerating the FPGAs, because then it's your proprietary, you can accelerate
Yes, yes.
with the hardware.
Yes, yes.
Whereas in GPUs, you have to rely on NVIDIA.
No, we have GPUs. They are upcoming.
Oh, they're upcoming?
We have everything.
Okay.
Sir, I have some questions.
Yeah.
Yeah, so the GitHub is not that great. The links that you have shared, most of them point to like a lot of defunct links, so just looking at it. So if you really want this to be adopted, I guess please work on it.
Thank you. Yeah, that's true. So we are like group of 6 people, not even 6. So we are running at a very high pace, but we are lagging. So
If
I
you
take
want,
that feedback.
if you want manpower, I think we can put some students with you
Yes,
on this.
we are
It's
doing
not a
it.
problem at all.
Yeah.
Second question is this x86 architecture dependent, or is this specifically Intel x86 architecture dependent? So for example, nowadays, unfortunately, you guys must have known this, Intel has been losing out to AMD on the server side, because the core per dollar is much better with AMD. So does this work on AMD CPUs as well?
It does work on x86.
Okay.
Any x86.
In any x86. All right.
Right.
So I have a
Hello everyone, welcome to the afternoon session, and this is the last